we're going to talk about Euler's method. We're going to start off with this situation. So we have y prime is equal to capital F of x and y. So the derivative of y, or the slope of the graph at a given place, could be dependent upon the x value and the y value. All right, so another way to think about this is also dy dx. That's the slope of the graph. All right, so Euler's method is just a way for us to approximate a particular solution, and it's useful because there's a lot of differential equations that we aren't able to solve. Either we just don't know how to solve them currently. In other words, we don't know the techniques to solve that differential equation. There are also differential equations that are unsolvable. So it doesn't really matter which of those categories we find ourselves in. Either way, Euler's method is a good way for us to get an approximation of a particular solution, maybe a way for us to get an idea of what that particular solution might look like. So it's really just an application of using differentials over and over and over again. Okay, so similar to the differential problems we've done. So we have to start at some point. We need a starting point. So we're going to start at some particular point, and we want to estimate the location of some other point on this function whose derivative we know, but the function itself is unknown to us. All right, so we're starting at this point, and in order to get a new y value, we're going to move some distance over horizontally to a new x value, and we're going to take the old y value and add the slope at the point we know times the change in x, or the differential of x. All right, so this right here is our good old friend dy. All right, so the new y value is just equal to the original y value plus dy, our estimate based on a linear approximation of the new or of the change in y. All right, so we calculate that slope, multiply it by the change in x, add that to the old y value, we get a new y value. So now we have this new point, x1, y1. We use that as our starting point for the next step. So we move some distance horizontally to the new x value, x sub 2. To find the new y value, we take the original y value, our y1, the one that we got in this step, and we add the new slope, or the slope at the new point, times the new differential of x. This is our new dy. So the old y value plus dy gives us our new y value. Now we have the next point, and so on. So we can take as many steps as we'd like. You can imagine if you think about making a linear approximation of a nonlinear function, the smaller we make our dx, the more accurate this process is going to be. In other words, the better estimate of the final point we get will be. So if we have the computing power or the time, then we would like to take many steps with a very small dx, and we can really get very good results from this given the function is reasonably behaved. But if we try to use large changes in x, then we're gonna leave the true function pretty quickly, and we'll have a pretty bad estimate. So just so you know, as you look at those problems in the book calls dx, it calls it h, so it's some horizontal distance that we're moving, which is fine. You can see probably that this process isn't so much hard as it is just very tedious and repetitive. So it's a really great use of computers, because computers are really fantastic at doing simple things repeatedly. We're going to do an example of this on the next page, so you can kind of see how it works out with the actual example.